Hello fellow engineers, today we will be discussing the applied calculation of a half-wave rectifier with resistive plus inductive load. Now a half-wave rectifier is usually operated with just a resistive load, which means a half-wave has been cut off and then a half-wave for the positive half cycle will move on while the negative half cycle will be cut off. Now when an inductive load comes into play, the circuit reacts differently. In order to find that out, we will perform a calculation. According to our question, an impedance of 10 plus j 5.7735 ohms is given, an RMS voltage of 230 volts, frequency of 50 Hz. We have to find out the expression for the load current, draw the output voltages and current waveforms, find out the mean output voltage and the mean output current. In order to perform our necessary calculation, we'll need a little bit of working to do. First of all, we have this RMS voltage and we'll have to convert it into our peak or the maximum voltage. Next, since we have Z, this is in polar form, we'll have to rectangular form, we'll have to convert it into a polar form. That means we have to find out its magnitude and its angle. The magnitude and its angle are calculated. Now since it is an RL load, it'll also have it'll not only have a steady state component but also a transient component. So for the transient component, we'll have to find out its time period or tau. Now since we have all of our values, we'll perform our necessary calculations. In order for our expressions, we need the output waveform, the output expression, right? So since we know that the circuit is composed of a steady state component and a transient component, both will be added to play. So the steady state component will be calculated using Em upon Z sine omega t minus theta, while the transient component, since it dies out, is an exponent term. After its necessary calculations, we have our values. Now coming to our graphs. Since this is a resistive plus inductive component, first of all, for the first positive half cycle, what happens is that the positive of the terminal is on the top and the negative is at the bottom, which means this diode is forward biased. Since it is forward biased, what will happen is the voltage across the supply will automatically go towards the load, assuming that the diode is ideal. So we'll have the output voltage will be following the input voltage for 180 degrees for the positive half cycle. Now when it comes to a negative half cycle, the waveform, the diode should cut off. Now since we have an inductor, the inductor's property is to resist the change in current. Now since the polarity has changed, the inductor will however resist it. For how long? For the angle duration of theta. So the waveform is to be followed for another 30 degrees. Why? Because that is our theta angle. This is for our voltage. Now for our current. Since we have three different components, a steady state, transient and the output current. So the steady state component, since it is an RL load, will be out of phase by 30 degrees. So this is our maximum for the I steady state. Now since this is at lagging, since it is not in phase, it will be lagging for 30 degrees. That's our theta. The transient component will start at maximum and will die out as soon as the current reaches its maximum value. Okay. Now since we know that I naught or the output current is the sum of these two, it'll be the added sum of both of these until they both die out at 0, which is at 180 plus theta, as indicated by our voltage graph. Now coming towards the mean voltage calculation, mean voltage is to be calculated using this formula, which means we'll have to find out the voltage time area or the integral of the wave and divided by the period of repetition. Now since the graph is running from theta 1 is 0 to theta 2, which is 180 plus 30 degrees, or if we put it simply, pi plus theta. So this will result in this following formula, and our period of repetition is 2 pi by omega. How is it 2 pi by omega? Because this entire cycle will repeat after 360 degrees or 2 pi. which gives our mean voltage at about 96.6, 96, 97 approximately. Now coming towards our steady state, our output mean current. For output mean current, we'll have to calculate the mean current of steady state as well as transient. Again, for integrating those graphs, since the steady state graph for the current and the voltage graph are kind of similar, we can either put it as mean voltage divided by impedance, or we can just calculate it by the following formula. Okay, coming to our transient. For the transient, since we know that we'll have to integrate it, we'll have to integrate this entire transient current for our values, which is from 0 to 180 plus 30, 180 plus theta, divided by omega. Why is it omega? Because we'll have to convert it in terms of time period, which comes out to be 1.29 ampere. Now since we know that our output mean current is the sum of these two, we'll add them up, getting our current of 9.6 amperes. Coming towards its simulation, we can see that the voltage is about 96, 97 ish, the current is about 9.6, and this is the output.